Hi everybody, this is Luke D, and this is Bio 2013, Molecular Bio Thought. So today we're going to talk about proteins, and proteins are actually pretty cool because they do a lot of things, and they're responsible for a lot of what you are. So right away, let's just talk about basic things here. Proteins are made of amino acids. That means if you see the word proteins, it is made of a set of basically the same repeating unit over and over again. Just like a centipede has parts, just like Legos have parts, just like, I don't know, something else has parts. I'm trying to look for something in the office that has parts. But the basic part of a protein is an amino acid, and it's called an amino acid because the left side of it has an amino group, and the right side has the carboxyl group. Now, right away, we should know there's something kind of not right about this. If this was in water, there should be an extra H here, so this would be NH3 plus, and this should be O minus. So this would be C double bond O, O minus, and an H plus out here. You can put two of these things together by something called a dehydration synthesis. So you basically remove one of these OH groups and you take away this H and you hook those two things together, and then you end up with a carbon bonded to a nitrogen and a extra water. That's why it's called dehydration synthesis. You took a water out of it. Don't let that term fool you, because I think sometimes when people think dehydration, they think taking apart, because like dehydration is negative and so is taking apart. But think about dehydration synthesis. So synthesis is making, dehydration is taking the water out. Okay, so that's how we take two amino acids and we put them together. We call an amino acid because one side is an amine group and one side is a carboxyl group. And the carboxyl group, when you put it in water, actually is an acid. It donates the high H plus and it becomes COO minus. Cool. What we're going to see over and over again is that if you look in a protein, you'll see this pattern: NCC, NCC.
Okay, so let's look at amino acids here. Now, I said look for the CCN, and we're going to do that right now. So C, C, N. You have the OH coming off this carbon and the double bond O, which makes this a carboxyl group. Remember, this is not a hydroxide group. This carbon, which we call the central carbon, it's bonded to a nitrogen, which will have two H's. Now, in high H hydrogen ion situations, actually, which water is one? Actually, water is about balance. So in that situation, this will pick up a hydrogen, and this will give off a hydrogen. So if there's tons of hydrogens around, then this carboxyl group will keep its hydrogen, and then you'll still have an extra hydrogen there. And if there's really, really no hydrogens around, then you'll have this nitrogen give off its hydrogen, and this carboxyl group will keep its hydrogen. Okay, so again, let's look. Carboxyl, carbon, amine group. All right, now let's look at another one. We got carboxyl, carbon, amine group. Oh, and we got that little hydrogen. Is that the same? Yes, it is. I don't know why I'm talking like this, but it's the same in these two. What's different is this top piece. Here, it's a methane group, methyl group, and here it's a sulfhydryl group. And that's kind of what makes amino acids different. It's just going to be this R group. Everything else is going to be the same. But that makes a huge difference in the way they act. So this chain, or this part, is going to hang off the side of an amino acid. And if this part is polar, then you have an entire molecule that's polar. If this part is nonpolar, you can have a molecule that's partially nonpolar and partially polar. If it's basic or acidic, so it could be a plus or a minus, and then you could have this side that's plus or minus. So amino acids can actually take on a lot of different characteristics. The R groups are going to generally be in one of a few categories. They're either going to be positively charged, so that means that they are an base, negatively charged, which means they're an acid. They're going to be hydrophobic, which means there's going to be lots of carbons and hydrogens, or they are going to be hydrophilic, which means they're going to be partial charges all over the place. All right, so let's look at one more. Here we have a carbon. So carbon, carbon, nitrogen, there's my pattern, carboxyl group, amine group,
Solomon Taylor and Rachel Davis, please go to the records office.
Oh, Rachel Davis. Okay, so then you have a carbon here and you have two oxygen here. Anytime you have an oxygen next to a carbon, you're going to know that the oxygen is going to be negative and the carbon is going to be positive. Anytime you have a carbon next to a hydrogen, you know they're going to be about of equal electronegativity, and so they're going to be neutrally charged. Okay, so carbon to oxygen, oxygen is going to be negative, carbon is going to be slightly positive, and this then will be slightly, wait a second, that's missing some things. That should have some hydrogens on it. Let's do another one. There we go. There we go. Better. So this will have slightly negative properties up here. This nitrogen will have slightly negative properties here. So this would be partially charged.
Charlie Beeman, please go to the McRae Theater. Charlie Beeman to the McRae Theater.
Okay, so why don't you try one? This one's a kind of tricky because it might throw you for a loop. You might think it's a nucleic acid, but you got to look for that characteristic CCN again. Did I do everything? Oh, yes. There's 20 essential amino acids. That means you need 20 amino acids that you cannot make. Is that right?
There are 8 that you can't make.
There are 8 that you can't make. There are
Those
20.
are essential. The other 20.
Right, sorry. All right, so I totally messed that up. Mr. Maxwell's here. So there are 8 that you can't make. Those are essential. So without them, you will die. Actually, if you watch the movie Jurassic Park, they made those dinosaurs so they couldn't make lysine, I think it was. So if they didn't eat corn, which is high in lysine, they would die out. So they could never get off that island. The other 12 we can synthesize, and that's about it. If ever you're trying to figure out exactly what an amino acid is or what it looks like, go to this highly reputable source, Wikipedia, type in amino acid, and it will give you a nice handy dandy chart that you can see here. You can blow that up a bit, and there it gives you amino acids that are electrically charged, so positive, negative. Here you have uncharged, so these are hydrophobic. These are special cases, so cysteine, for example, which is going to be the disulfide bridge. I have selenocysteine, I have no clue what that is. Here you have, I'm sorry, this is hydrophobic. Oh, this is just uncharged. Okay, so this is hydrophilic. So just one note, if you have a chain of hydrophobic amino acids, so that means you have lots of R groups coming off of a protein that are hydrophobic, then it's going to be, that protein chain is going to be able to do things in lipids that normal ones won't be able to. Okay. Yeah, that's it. Promise. Okay, so you may have understood all that stuff, and now you may be looking at this and going, what is happening here? And I'm going to try to explain that to you. So a lot of times we look at proteins like this. This is a simplified version of what it actually looks like. So let's start with what it actually looks like. And I noticed, by the way, that my ability to talk and work the console don't work well together. So forgive me if I take a while to do this. Nope. All right. Control, console, editor, console. Okay. And let's make this one go away. And all right, good. Okay. So we're going to go ahead and select all, cartoon off, wireframe 100, and there you go. That's what the whole thing looks like. Now this is way too confusing to be able to figure anything out about. As a matter of fact, even though I know the structure of this protein very, very well, I know that it's insulin, I couldn't recognize it from this shape. I might be able to, maybe because I might know where the disulfide bridges are here, but probably not. So let's start with the way I've told you to start. Oh, poo. Select, okay, hold on, console, editor, console, okay, go ahead. All right, let's try that again. Select not backbone, and then we're gonna go wireframe off. Okay, so what this is gonna give us is our basic patterns of C's and N's. You can see it, hopefully you can see it in there. Carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen. So this is just our backbone. Now, this is going to give us a basic idea of what we're looking at because it'll give us the shape, or the basic shape at least, of the protein. I love Max. Okay, so cartoon 50. All right, so you can see that kind of that ribbon that's been drawn in there. That's the cartoon, and so what it's following is the backbone. So when you see that cartoon, you're going to know from now on that that's actually just the backbone. Now, what's left? Okay, well now I have all my R groups that aren't on here, and they're going to be really big reasons, or part of big reasons, why this thing folds the way it does. But I want you to take a look at a couple structures really quickly. So okay, so I want to look at all right, so if you look in this cartoon here, you have the string kind of going in a little circle, or a loop-de-loop, and that's a helix, and you guys have seen that before. And that's a really, really common and stable structure for a lot of amino acid sequences, or a lot of proteins. This specific helix is actually caused by interactions specifically between the backbone and itself. So this oxygen, which is negatively charged, is going to be attracted to this hydrogen, which is positively charged. So we call this a secondary structure. Now, it does usually happen pretty quickly, but it doesn't necessarily always happen second in the order of things. But what I need you to know for this is that alpha helixes, when you see them, are caused by attractions between the backbone and itself. What do we differentiate that between? Well, the R groups, all right, so are going to be responsible for the rest of the shapes. So select backbone, wireframe off. Okay, and then select not backbone, wireframe 50. Okay, so this is everything else. These are all the R groups, and they're not connected right now to the main backbone. I haven't put that back in yet, but these are going to be responsible for all the other shapes that you see here. Anything other than basically two shapes, the helix that you've seen here and you saw unfolded, and the beta pleated sheet, which you've also seen unfolded. It's all going to be because of positives and negatives that everything is attracted, but in the end, R groups are going to be responsible for the majority of the folding of a protein, and then the alpha helix is going to be the alpha helix, or the beta pleated sheet, right there, alpha helix, is going to be backbone-backbone interaction only. Okay, so the rest of this can be between an R group and the backbone, or between one R group and another R group. So that should give you a better idea of what you're looking at when you're looking at this guy. So you should know just by looking at this thing that this helix is the CCN being attracted to itself, that the other parts of this are caused between attractions between R groups that are hanging off of this cartoon thing that you can't see right now, and other R groups or the backbone. I hope that all made sense. Your reading should really help you, and we'll go over this in class. As a matter of fact, interrupting these R group interactions and the backbone interactions is exactly what you're trying to do now in your lab. So have a good one. Bye.